Hello guys, welcome to another discussion video. In today's discussion, we are discussing physics SDA paper 3 2021. Okay, so if you're interested in revising one-on-one or as groups, there is a link. Okay, I'll post the link to the WhatsApp group where you can participate as a group member, and also you can receive links to online classes that happens on a daily basis. Okay, so the prices and everything is posted in the pinned video that you can see there. Okay, so the first question says figure 1.1 show the scale of force meter used to measure the weight of a wooden block. A, define weight. What is weight? So weight is simply the amount of gravitational force pulling on a mass. Okay, we can just write here gravitational force pull on a mass. Okay, mass. Okay, next one. B, record the weight of the wooden block shown in figure 1.1. So it's very important to understand scales. Okay, whenever you are looking at a measuring instrument, you should be able to decipher or to analyze how the scale works. Okay, so from here we have a 0 and then you have 5 here. So that means between 0 and 5 you have those other numbers that are found between 0 and 5. Okay, so that means the larger denotions there or divisions there, it's in ones. Okay, so that's 1, 2, 3, 4, 5. Okay, and then the smallest division there will be a 0.5. Okay, so therefore if you are counting everything there, that means your scale is going to be going from, or your readings are going to be 0, 0.5, 1, 1.5, etc, etc. Okay, so let's just zoom in here so that you can see. So here this is 1, this is 2, and then that's between 1 and that's between 3 and 2. So that means between 2 and 3 it's what? It's 0.5. Okay, so that means it's 2.5. so our answer is going to be 2.5 watt newtons. Okay, newtons. C says calculate the mass of the wooden block. Calculate the mass of the wooden block. So what is the formula that we are going to use? We are going to use this triangle, force A M. Okay, now this the force is going to be our weight, and then A, acceleration, is going to be acceleration due to gravity. So we can rewrite this with respect to the force that we have and also the acceleration that we have. Okay, so the force is weight, and then acceleration is g, acceleration due to gravity, and then mass is mass. What are we looking for? We are looking for the mass. Okay, so mass therefore is equals to weight over acceleration due to gravity. Our weight is here, so 2.5 divided by acceleration due to gravity is 10, so we just move this there, and then our answer is going to be minor error. So we're dividing, so we move the decimal place in front there, so that our answer is 0.25. What are the units for mass? Is going to be kilograms. Okay, because this is 2.5 newtons, and then this is 10 newtons per kg. Okay, so the newtons cancels newton, and then we're left with kilograms. Next question says the wooden block is raised to a vertical height of 10 meters above the ground. Calculate the gravitational potential gained by the block. Okay, so what is gravitational potential energy? So basically, gravitational potential energy is the type of stored energy that we get when you raise a piece of matter or mass above the ground. Okay, so let's say this is the ground. Okay, this here is the ground, and then you take something and then you elevate it. Okay, you bring it to a certain height above the ground. Okay, now by doing that, you are creating, or there's going to be that mass is going to have potential energy, gravitational potential energy. So gravitational potential energy simply refers to stored energy of an object that has been raised above the ground. Okay, so how do we calculate that? So the formula is gravitational potential energy, that's the abbreviation, is equals to mass times acceleration due to gravity times the height. Now what is the mass? The mass, we found it on the previous question, 0.25 multiplied by, maybe let's just add units so that you can see how the units cancel out. Okay, so this is kg times acceleration due to gravity, which is going to be 10 newtons per kg, times the height. The height is 10 meters. Okay, so what are we cancelling? We're cancelling this, that, then we are left with Newton meter. All right, so calculating everything, so times 10, you move the decimal place one time, times 10 again another time, so that you get 25 Newton meter, which is going to be joules. Okay, so energy, units for energy, it's joules. Okay, all right. Question 2 says, so here we're looking at thermal physics. Okay, shows a figure 2.1 shows a pot used to boil water. Define boiling point. What is boiling point? So boiling point is a temperature. Okay, temperature. So this is the temperature at which a pure substance changes its state from liquid to a gas. Okay, liquid to a gas. Let's just put that in there. Okay, so boiling point, it's a fixed temperature. Okay, it's a fixed temperature at which a pure substance, okay, at which a pure substance changes its state from liquid to a gas. For example, water boils at 100 degrees Celsius. B says, water droplets are seen underneath the lid when it is lifted. Name the process that leads to the formation of water droplets. So how do you form water droplets? So to form water droplets, first you start off with steam. Steam is a gas, and then you change to water droplet. Water droplet is liquid. So this process here is simply condensation. Okay, this is condensation. Okay, all right, and then we continue. C says, complete table 2.1 by stating two differences between boiling and evaporation. What is the difference between boiling and evaporation? Now we have to look at the temperature at which these different processes occur. The temperatures at which these different processes occur. So now boiling happens at a fixed temperature. So this occurs at a fixed temperature. Okay, for example, water boils at exactly 100 degrees Celsius at sea level. Okay, at sea level. Whereas when it comes to evaporation happens over a wide temperature range. Okay, so this occurs, or this process happens at various temperatures. Okay, temperatures. Okay, so evaporation occurs at various temperatures. This is why you can get water evaporating from a lake during winter, and then you still get the evaporation happening during summer, even in places that are very, very cold, like in the tundra regions. You get water evaporating, but the average temperature in those areas could be below zero, slightly above zero, and then in the savanna or in the tropics, you get the temperatures rising all the way to 35 plus and all that. Okay. However, with boiling, you know that boiling, depending on the elevation, or just let's just say at sea level, water will boil at 100 degrees Celsius. No, now that is fixed. Okay, that is going to be fixed. Pure water, of course, we are looking at pure substances here. Okay, now the question is, where does boiling versus evaporation occur? Where does it occur when you're looking at a liquid? Okay, so when you're looking at a liquid, boiling occurs throughout the liquid. Okay, so this process happens through the entire liquid. This is why when the water is boiling, you see the water kind of like bubbling like that. Okay, it's because that process is occurring throughout that liquid. Okay, so occurs throughout the liquid. Occurs throughout the liquid, whereas evaporation only happens at the surface. Okay, so it only happens at the surface of the liquid. Surface of the liquid. Okay, so evaporation happens only on the surface of the liquid, whereas boiling happens throughout the liquid. Okay, so it's very important whenever you're describing these processes. What's very important is the keywords. Okay, keywords are very important because most of the marking is based on the keywords, not your ability to construct sentences or all that. The keywords, the use of keywords. Okay, and then this says thermal energy is transferred through the water inside the pot by convection. Describe the process of convection. What is convection? How does it occur? Let's start with the diagram. Okay, so when you have water, let's say this is the pot. We're making a diagram of that pot. Okay, so this is our pot. Now, what's going to be happening here is that you are heating here. This is the heat, H for heat. Okay, then this is your water. I'm going to throw in a bunch of arrows in there to show the convection currents. Okay, so those arrows usually represent convection currents. Then I'll paint this area blue. No, not blue, red. Okay, so let's paint it red. Okay, not blue. We'll paint this part red because that's where you are heating. Okay, that's where you are heating. Then we'll paint this area blue. Okay, it will make sense in a minute. Okay, now what's happening when you're heating the water? When you're heating the water, first of all, the water molecules at the bottom of the container are going to gain heat energy by conduction from the fire. Okay, they gain heat energy by conduction from the fire. Now when they are heated, they expand. Okay, the water molecules there, they expand. What does that mean? It means when you have, this is a typical water molecule, H, so you'll have a bunch of them loosely connected. Okay, remember your chemistry, loosely connected like this. So you have a bunch of them around this area, loosely connected by these forces here. So those are the intermolecular forces. Okay, now when you are heating the liquid, these forces here, okay, these forces here, they get broken up. Okay, so this causes this water molecule to move away from the other water molecule. Okay, so overall area that these water molecules are covering is going to be what? Is going to increase. And then you know that from your formula that density is equals to, density is the amount of substance per unit volume. Okay, so mass over volume. Okay, now if the area increases, therefore the general volume of that area is going to increase. Okay, now if you have more of the volume per fixed mass, then your density is going to decrease. the value of the density that you get there is going to decrease. Okay, so the expansion of those water molecules, or the water molecules moving away from each other, causes the water in that area to do what? To become less dense. Okay, to become less dense. All right, I'll borrow the space here. So if they become less dense, what's going to happen? If something is less dense than its surrounding components, what's going to do? What's going to happen? That less dense water is going to rise. Okay, it's going to rise. And then on the contrary, this area here, we do have cool or colder water. Okay, so cold water is more dense. Okay, is more dense. Why is it more dense? It's more dense because the water molecules in that area are close to each other. Okay, they are close to each other. Are we together? They are close to each other, overall covering a small area. Then we go back to our density formula. Density is equals to mass over volume. So if we have the volume or the area, remember the area in 3 dimension gives you the volume here. So if you have a small volume, then you are getting what? You are getting more density. Okay, this is why cold water is more dense, because the water molecules are close to each other. So you have more water molecules per given area. Okay, yeah. Now what does that mean? It means that the cold water is more dense than the warm water, therefore it sinks, and then this cycle can repeat over and over again. So that's the explanation. Now we're just going to write it in terms of just the answer. Okay, so for those who know what the explanation is too much, you can just skip to the answer. The explanation is for those that are doing triple. It's very important that you understand the physics behind why they are convection currents occurring. Okay, so let's just write our answer here. Water at the bottom gains heat energy by conduction and expands. Expanded water is less dense, hence it rises. Okay, it rises. The cold water above sinks as it is more dense. Then subsequently this process repeats, creating convection currents. Okay, so that is the whole process. Okay, what do we need to acknowledge from there? What we need to acknowledge from there is you acknowledging the different temperatures in the water. Okay, you have warm water with its less dense density, and then you have cold water which is more dense. Okay, so the warm water is less dense, so it rises. The cold water or cooler water it's more dense, so it falls. Okay, cold water more dense, it falls. Warm water less dense, it rises. Okay, question 3. Figure 3.1 shows a ray of light moving from air into a glass block at an angle of 55 degrees from the normal line. The angle of refraction is 33 degrees. The diagram is not drawn to scale. give the meaning of angle of refraction. What is angle of refraction? So the angle of refraction is simply the curvature formed, okay? The curvature formed away from the normal by a light ray as it enters the medium of different refractive index, okay? Now you see that this is the incident ray, okay? This is the incident ray, and then now this is our angle of reflection, okay? So that's our angle of reflection. Now when we define this, let's simply define it here. When we define angle of refraction, an angle is a curvature. So we can say, you know, an angle of refraction is the angle of, okay, so we just say curvature. So instead of saying angle, you can just say curvature. Curvature formed, okay, formed between, okay, between the normal. You know what the normal is, right? This is the normal line, okay, the normal line. So is the curvature formed between the normal or let's say away from the normal. Let's add here, formed away from the normal by a light ray entering a medium of different refractive index, okay. So as you can see here, you have this light ray from medium 1 entering medium 2. As it enters, the light ray deflects, okay, deflects away from the normal altogether. So it deflects away from the normal, forming this curvature here that I'm shading, okay. So therefore the refractive index is this curvature here that is formed between, okay, or away from the normal line, okay, from the normal line by a light ray that is entering a medium of different refractive index. So that's that. Calculate, let me just remove this. Calculate the refractive index N of the glass block. Okay, so how do we calculate that? You need to know the formula. So the formula is N refractive index is equals to sine angle incident angle, okay, over sine refractive index, okay. So this is going to be sine. What is our angle of incidence? Angle of incidence is this side, so 55 degrees over sine refractive angle is 33. Put the 33 there, okay, and then you just punch that into the calculator. You get 1.504. okay, so this does not have units, so correct to 3 significant figures, 1.50. so that's our refractive index. C says the frequency of the light is 6.0 times 10 to the power 14 hertz. The speed of light in air is 3 times 10 to the power 8 meters per second. Calculate the wavelength of the light. So here you just need to know the formula, okay, you need to know the formula. So the wavelength formula is that V is equals to frequency times lambda, okay, frequency times lambda, which is the wavelength. Now you just make wavelength subject of the formula, so divided by f, the frequency, okay. Therefore wavelength is equals to, or is given by, the velocity of light in air over the frequency, okay, over the frequency, which is going to be equal to the velocity of light in air 3 times 10 to the power 8 all over frequency is here 6.0 times 10 to the power 14 hertz, and then you plug that into the calculator, you get 5 times 10 to the power 21 meters. Okay, so wavelength, it's length, so it's measured in what? It's measured in meters. Okay, also when you cancel your units here, you should be able to get meters. Okay, should be able to get meters. All right, let's continue. Name two regions of electromagnetic spectrum other than visible light. So the way you remember this, you just write ga to v mira. Okay, you should be able to get all of them here. So this is gamma rays, X-rays, ultraviolet visible light, microwaves, what else? Yeah, etc. Okay, so this can help you remember some of those electromagnetic spectrum components. Okay, so this is radio waves. Okay, so we can write X-rays, we can write gamma rays. So this is like easy marks, so just use this abbreviation GATU VIMIRA to try to remember them next time. All right, so move on to question 4. Figure 4.1 shows a symbol of an electrical component. Figure 4.2 shows a voltmeter connected across the component. State the name of the component represented by the symbol in figure 4.1. What is that? What is going to be a cell? Now, what's the difference between a cell and a battery? A cell, just one single cell like that. Okay, so it has just this. For the science, it's just that. Okay, then what is a battery? A battery is when you put two or more cells together. Okay, so if we were to do this, let's put 1, so that's one cell right there. Okay, but if we were to connect another cell like this, now it has become a bit. Okay, now it has become a bit. Now the only thing that you need to be careful about is the length of those dashes. Okay, so if you're starting with the taller dash, which is your positive, you should end with the smaller dash, okay, which is your negative, so that your battery's terminal is plus negative, not plus plus. Okay, because to make a battery, you're just adding what? Bunch of cells side by side, okay, or back to back. Roman figure 2 says, state the purpose of a voltmeter in an electrical circuit. State the purpose of a voltmeter in an electrical circuit. So the voltmeter is there to measure the potential drop. Okay, so it's there to measure the potential drop. So let's say you have the voltmeter. Let's say it's connected to something. I'm just going to add it here. Let's say it's connected to a light bulb. Okay, yeah, maybe let's say it's like that. Maybe let me just draw it here. So you have a light bulb here, and then you connect a voltmeter here. Okay, connect a voltmeter. So what's going to essentially happen is that inside the voltmeter, it is going to detect the amount of voltage coming from this side. Okay, let's say it's 50 volts, and then on the other side is going to detect how much voltage is coming out of that. Okay, after the current has passed through the bulb. Okay, let's say it's 20 volts, and then the voltmeter will calculate the potential difference, basically the difference, how much of the voltage was used up inside the bulb. So it's 50 minus 20, which is going to be 30. So the voltmeter reading is going to show what? 30 volts. So then from there you can say, oh, the bulb uses around 30 volts, or it uses 30 volts according to our voltmeter. Okay, all right. B, figure 4.3 shows a circuit diagram. Okay, we have our circuit there, What type of circuit is that? That will be a series circuit where everything is connected in just one loop. Okay. The reading of the ammeter A1 is 0.10 amps. Determine the reading of ammeter A2. So the reading on ammeter 2 is going to be the same. It's going to be 0.10 amps. Why? Because in a series circuit, current is the same throughout. Okay. Whereas in a parallel circuit, current is added. Okay. Current is added. Then Roman figure 2 says, calculate the total resistance of the circuit. Calculate the total resistance of the circuit. So how do we calculate the total resistance of the circuit? So to calculate the total resistance of the circuit, in a series circuit, resistance is added. So RT is going to be equal to R1 plus R2 plus Rn. Okay, which is equals to R1 is what? It's 20 ohms plus R2 10 ohms, which is going to give us 30 ohms. 30 here. Then we continue. Roman figure 3 says calculate the potential difference across the 10 ohms resistor. What is going to be the potential difference? Now to calculate that, we use our triangle VIR. We are looking for what? For voltage. Okay, so voltage is equals to I times R. What is our current? Our current, remember, it's 0.10 times. What is our resistance? It's here 10. So 10, and then we get 1 volt. So just plug into the calculator then. 5 says, figure 5.1 shows a transformer. So that's the transformer. State the type of transformer shown in figure 5.1. Now the type of transformer that we have there, that is going to be a step down. Okay, a step down transformer. Why are we saying it's a step down transformer? Just know that you can just look at the coils. Okay, you look at the coils. So you have more coils versus less coils. Okay, so if you're moving from more to less, you are stepping down. Okay, you are reducing, hence step down. Again, then if you're moving from fewer coils, like the opposite, if the fewer coils was on the left side, then it's a step up, because you're stepping up the number of coils. Okay, so you can just use the coils to remember all that. Okay, to remember all that. B says the transformer has a primary voltage of 240 volts and secondary voltage of 6 volts. The number of turns in the primary coil is 1100. Calculate the number of turns in the secondary coil. So here you need to use your transformer equation. Okay, so it says voltage 2 over voltage 1 is equals to number of coils over on 2 versus over number of coils on 1. Okay, so you can identify your parameters. So V1 N1, V2 N2. So voltage 1, remember the one part is the primary part, and then 2 part is the secondary part. Okay, so primary is going to be V1, secondary is going to be V2. Okay, so voltage 1 is 220 volts. Then the number of coilings is going to be what? The number of coilings is going to be 1100. Then voltage 2 is 6 volts. Then N2 is going to be what? It's going to be unknown. So we leave it as N2, and then we make N2 subject to the formula. Okay, so let's just remove this arrow, then just substitute into that equation. So V2 is 6 volts over V1 is 220, which is equals to N2 unknown, so we leave it as N2 over N1. N1 is 1100. So you can just multiply by 1100 times 1100. So cancels that. Therefore, N2 is equals to 1100 times 6 all over 220. Then you punch that into the calculator, you get 330. Now those are the number of what? Those are the number of coilings, okay? So they don't have units. Give a reason why electricity is transmitted from a power station to consumers at high voltage. At high voltage. Why is it? So now when you are transmitting at high voltage, you are moving less current, okay? So current can cause the heating up of cables, okay? So this is to prevent heating up of cables, okay? Prevents heating up of current of electric cables. Okay, now of course there's more to the story. The idea is that when you're transmitting at high current, you're going to have that current heating up the cables, okay? Now when it heats up the cables, that means that the electrical energy is being converted to heat energy, therefore losing what? Losing the overall amount of electric current that you can deliver to the customer. Okay, so this is to prevent, one is to prevent the heating up of electrical cables that can result in fires and all that. And also it saves, okay, it saves the overall amount of electrical energy that can be delivered, okay, that can be delivered. So that's the other reason there. So we're about to conclude here. I think this is the last question. D says, figure 5.2 shows another transformer with a 12 volts direct current connected to the primary coil. The switch S is closed and the pointer in the galvanometer deflects and rapidly returns to the original position. Explain why the pointer deflects when the switch is closed. Now, when the switch is closed, here we're looking at an electromagnet, okay? We're looking at an electromagnet. So when the switch is closed, the current is complete, okay? Sorry, the circuit, not the current. The circuit is complete. What does that mean? It means that now the flow, okay? The flow of current in this circuit can happen, okay? Now, the current flows across the coil, which induces what? Which induces magnetism, okay? Remember how an electromagnet works, okay? Or the interaction between current and magnets. We know that when current is flowing through a magnet or across a magnetic field, it induces what? It induces current. If a magnet is moving, okay, it's moving across an electric current field, it induces what? Current. I get So here we can just say that when switch is closed, the circuit is complete. That's the first part. Maybe let's write that down. When switch is closed, when the switch is closed, this allows for current to flow across circuit, which induces magnetism. Okay, so it induces what? It induces magnetism, right? It induces magnetism on what? On this core here, okay? So it induces magnetism on that core there. Are we together? So it induces magnetism on that core. Now this core now is temporarily a magnet. Okay, the core is now what? Temporarily it's now a magnet. Okay, now this magnet has a magnetic field. Okay, it has a magnetic field. Now as that magnetic field is being created, it's going to do what? It's going to cut across this area here. Okay, it cuts across that area. Therefore inducing what? Inducing an electric current on the second coiling here. Okay, inducing an electric current on the second coiling there, which is then detected by the galvanometer. Okay. When switch is closed, this allows for current to flow across the circuit, which induces magnetism on the primary no on the what am I saying, on the maybe let's just leave it at that. Okay, induces magnetism, and then we stop there. And then the second coil is within the magnetic field. Okay, the magnetic field and that magnetic field and the magnetic field induces electric current on the secondary coil now. Okay, secondary coil, which is detected by the galvanometer, Okay, I'll explain this one more time because I feel like I didn't explain it properly, and then that will be the end of that. Okay, so what exactly is happening here? Now you need to understand your electromagnet, how an electromagnet is formed. Okay, so we'll start with this primary part here. So when you close this circuit, current is going to flow. Okay, when the current flows, it's going to temporarily make this core to become a magnet, so it gets magnetized. Okay, now since this secondary coil is within the magnetic field, as the magnetic field cuts across those coils, it induces current in the coils. Okay, it induces current in the coils. Now that current is going to flow within the circuit, and then as it flows is detected by the galvanometer. So essentially that's exactly how it happens. Okay, circuit is closed, current flows, current induces magnetism. Okay, the magnetic field induces current in the second coil. The current in the second coil flows and is detected by the galvanometer. Okay guys, thank you for tuning in. I'll see you on the next one.